Have you ever wondered how to calculate the water depth in natural channels and how this depth would vary with different discharges? The problem exists because of the irregular shape of the cross-section and the non-homogeneous distribution of roughness along the wetted perimeter. The picture shows a cross-section of a natural channel. When the discharge increases in a channel, the water level tends to increase. As hydraulic engineers, we are interested in calculating the elevation of the water because this has a direct influence on the level of exposure of the surrounding environment. As water elevation increases, we need to take into consideration the varying frictional forces along the wetted perimeter, especially introduced because of side roughness. To solve this problem, we need to focus on the velocity distribution along the river's cross-section. We know that water velocity within a section is usually maximum towards the center and progressively decreases towards the sides. The reason for this velocity distribution is because of the influence of the channel friction and the shape of the cross-section. When the roughness changes along the wetted perimeter, we can adopt two different approaches which determines the velocity distribution across a river's cross-section. These two approaches are the unique and compound section approach. The accuracy of each approach depends on the type of cross-section which is being applied to. The unique section approach considers the complex geometry as one entity and assumes one velocity throughout the section calculated using an average roughness value. This method of approach is more accurate for this type of cross-section. Whereas, when dealing with this type of cross-section of even more complex geometry, the compound approach is more accurate. This approach performs section partitioning and introduces different velocity zones. Additionally, an alpha coefficient is used which tells us more about the non-uniformity of the flow within the cross-section. In order to adopt these two different approaches, we need to understand the properties and limitations in applications to specific cross-sections. In studying these concepts, we will learn how to choose between the two different approaches depending on the channel characteristics. Furthermore, we will understand the possible inconsistencies arising in the adaptation of the approaches to specific channels. At the end, we will learn how to evaluate the effect of roughness and shape on the velocity distribution and redistribute the discharges in order to calculate the water profile. Ultimately, this is a matter of accuracy and how much we can use a one-dimensional model to represent the two- or three-dimensional nature of the problem.